Hello all, welcome back to another video. This time we're going to be going back to geometry in this same book, a wonderful book. Now, let's go to the problems. We did problem 1 last time, so this time we're doing problem 2. So, just grab a picture of that, bring it over here, and as usual, we're going to do the same thing. Okay, first, of course, we need to draw it out. Okay, let ABC be a triangle. Okay, so first let's draw this triangle out. Maybe do something like this and this. Again, you want to make sure that you're not making it like a right triangle or an isosceles triangle, or make sure that there's no assumptions that might incorrectly be made. You want it to be just an arbitrary triangle. Now, like this may be kind of isosceles with these two sides, but it's close enough, and we have to make sure not to assume anything. And now let's just label it A, B, and C. Now let M be a midpoint on the ray AB beyond, sorry, not a midpoint, be a point on the ray AB beyond B, so down here, such that BM equals BC. Okay. Let's just draw that. So we'll say that's a horrible point, but M, and we can say this. Again, we're just going to write it out that these two are equal. Prove that MC, so let's draw that, is parallel to the angle bisector of ABC. So this, say this is approximately the angle bisector. We can see that looks about right. And again, to prove that's an angle bisector, we're just gonna do this. Or actually, another thing you could do instead is just label it with something, so you can always write it. So we're gonna call each of the things alpha. These Greek letters are usually what's used. So you have some things. Now, again, take some time, look at it, and try to come up with some ideas about it. Okay, now, again, we're going to come back to it, and I'm going to try and tell you my thought process right now. Again, I've not seen this problem before, so I'm just going in blind. I notice immediately that these two are the same, so this is an isosceles triangle, MBC. So, I'm just going to draw this, and I can maybe label this beta. Just draw these. Now we want to prove MC is parallel to, let's label this point B, say D. Okay, how would we do that? I'm trying to think right now. There's a lot of different parallel line theorems that we know. So let's see if we can try to use some of them. For example, if these two are parallel, we can say this is equal to this. So alpha is equal to beta. Already, that's something we can try and prove. So therefore, alpha is equal to this, and we can kind of see that that would be the case if these two are parallel. So, how would we do that? Okay. Looking at it for a bit, I noticed one thing with relation to this. I was thinking about this for some time, and then I noticed that these two are the exterior angle of this. If you didn't know, or not exterior, the external angle of this angle here. So therefore, these two must be equal to the sum of these two must be equal to the sum of these two. Or if you don't fully knew that before, you can see that this angle has to be equal to 180 minus these two, because it's a triangle, and because this is a line, it has to be equal to 180 minus these two. Therefore, these two have to equal these two. Therefore, 2 alpha equals 2 beta, or alpha equals beta. So, with that, we've pretty much proven it. If you really, okay, so now we can just go back on this. So we have this point D here. We can now say with certainty that alpha equals beta. And now that makes the job a lot simpler. Okay, so yeah, that makes our job a lot simpler, because we can say now this is equal. These two are now also alphas. Now one thing you can notice is with this angle here, triangle ABD has angle A and alpha. Triangle AMC has angle A and alpha. Therefore, they're similar to each other. So now then we can write, actually we don't need alpha equals beta now. We can also write that triangle ABD is similar to triangle AMC. Oh, actually, what am I saying? You don't even need the similar triangles part of it. Because one thing is, when you have parallel lines, you obviously have the idea that opposite angles are equal if you make this line here the transversal. Or if you make this line the transversal, you can see that this one and this one are both corresponding angles and they are equal. Now, if you don't know all of this, I would recommend looking at some videos. Other videos are out there, or looking at this same book, A Beautiful Journey Through Olympiad Geometry. It is a wonderful book to look at, this one right here, and it's perfectly free on the internet. Anyway, the thing is, you can also prove parallel lines using its converse. So because these corresponding angles are equal, then these lines are parallel. That's something I know for a fact. I'm not so sure about whether opposite angles works or not, but I do know if two corresponding angles are equal, the lines are parallel. Therefore, those lines are parallel, and we have our proof. Now let's actually write it down. Again, I always like to say that this is a very important part, writing the proofs out, because that's something that's very useful later in life, and it's a really good skill to develop. Even I'm not the best at it, but I'm just trying to show it all out to you guys. And if you have any tips, please give it to me. Now, okay, so think about what we did first. First, tell us about any points you've done. So D. So let D be the intersection of the angle bisector of ABC, of angle ABC, and the segment AC. Okay? Let the half angles of angle ABC cut by the bisectors, so basically these alpha ones, cut by the bisector. Cut by the bisector be equal to, we'll say X just for the simplicity here. I won't write out alpha or anything. So those are X. And then we can say, so obviously we had some things writing in betas and all that, but we can just make it simpler right now because this is a proof. It's meant to be concise and elegant. Let's say, notice that 2x is the exterior angle of angle, what's that, MBC. Thus, it is equal to the sum of the remaining two angles. Since MB and BC, these segments, are equal, so then, as we know, their corresponding I think that's how you spell it, angles are equal. Thus, 2x is equal to the sum of these two angles or double of one of them. Therefore, since it's 2x and double of one of them, each of those angles of those two angles, just to specify, are also equal to x. Actually, one thing I want to change, this can be a bit vague, so I'm going to actually change it to actually naming it y, just to be more their corresponding angles are let's say their corresponding angles are equal, them be known as y. Okay, so thus 2x is equal to the sum of y and y. So 2x equals 2y. And therefore, x is equal to y. Okay, good, we have that. Now, looking, oh wait, not capital. So now looking at, we want to look at these two, right, the corresponding angles. ABD, angle ABD, and angle, that'll be BMC. They are both equal, as we've said above. And then, how should we say this? I guess, notice, that's, as you can see, I like to use that they lie on BD and MC respectively, and they are both cut by AM. Thus, since these two angles are equal, they represent corresponding angles that are equal. So, by the converse of the corresponding angles theorem, and using the transversal, or not using, converse of the corresponding angles theorem, using the transversal AM, we can deduce that BD is parallel to MC. I think that's a decent proof. Again, if you have any tips for me, please leave them down in the comments. Anyway, I hope you enjoyed. I hope you learned a lot from this. I mean, again, just like in our last video, we talked about isosceles triangles and their corresponding angles. We talked about the exterior angles idea, and then we talked about parallel lines. And I hope if you were unsure about any of these, please look them up on YouTube. There's wonderful videos out there by a lot of good teachers as well. There's this book again, A Beautiful Journey Through Olympiad Geometry. And then of course, we wrote this proof out, which please give me some tips about it. Anyway, I hope you enjoyed, and keep on problem solving.